We've been using both integral and floating point types in our programs. By now, you've probably got the idea that we use an integer when we want to represent a whole number, and a double when we want to represent something that might have a fractional part. The computer uses a fixed number of bits to represent both these types, which limits the precision and the range of the values that can be represented. In this video, we'll further explore this idea. Here we have initialized an integer I with value 17 and a double D with the value 4.8. Let's print both of those values. What will happen if we assign D to I? We are assigning the value 4.8 to a variable whose type is an integer. We see that the fractional part of 4.8 is dropped, or truncated, and I gets the value 4. This is probably what you expected. But what happens when we change the double value to be really big, larger than the maximum integer that can be represented on my computer? Now the variable I can't represent the truncated value. It's too big. My C compiler doesn't give any warning. It just stores the integral value in I, but that value isn't helpful. You need to be careful when converting between types that the new type is able to represent the converted value. What if we assign an integral value to a floating point value? Here we assign 17 to the double variable D. It all seems good. 17.0 can be represented by a double. You might at first think that all integers can be represented by a floating point type. After all, the integers are a subset of the real numbers, so every integer is a real number. While that may be true in pure math, it isn't true using computer representations of numbers. We have to remember that we are implementing the representation of these values with a fixed number of bits. Let's change our program slightly and look at how many bits my computer uses to store an integer and a double. Notice that we use size of on a variable name to learn how many bytes are used by our compiler, and that the resulting value is printed with the LU format specifier. We see that on my computer an integer uses 4 bytes and a double uses 8. Let's do the same for a float. I won't run this code yet, but when I do, you will see that float uses 4 bytes. Now suppose I want a big integer. Int max, defined in limits.h, is the largest integer that my system can represent. In case you don't believe me, let's add one more. See that warning? The compiler knows that we're going to overflow the integer. And sure enough, we see a negative value when we print that variable. But now let's assign our big integer to a float variable. What do you think will be printed? Is that what you expected? It's off by 1. Let's try a different large integer. Oddly, there's a bigger difference. Remember that both the float and the int are using 4 bytes, so they can each have 2 to the 32 different bit patterns. That's 2 to the power of 32 possible different values that they can represent. So it isn't possible for the floating point number to be able to represent all those 2 to the 32 integers, and then also be able to represent various fractional values in between them. If the integer is larger than the float can precisely represent, it stores an estimate, a value that is accurate to a certain precision. So our unusual result isn't that surprising. Let's consider one more kind of conversion. Suppose we are converting between 2 different sizes of integral types. A char is represented by 1 byte. Let's print out the value of ch, interpreting the value as both a char, using the %c format specifier, and as an integer, using the %d format specifier. Now if we assign the value from ch, the char, to integer j, we know that j will be able to hold any value that was represented by ch. We can say that an integer is wider than a char. We will get what we expect when we run this code. But what about when we take an integer value that is too large to fit into a char? Let's make I 320 and see what happens. We see that 320 doesn't fit into CH. This conversion drops the higher order bytes, 256 in this case, and ends up storing 64, that's 320 minus 256, in CH. And 64 is the ASCII code for the @ symbol. The take-home message here is that you need to remember that integral values, integers, chars, shorts, longs, are limited in range, and that floating point values, floats, doubles, long doubles, are limited both in range and in precision. When you convert from one type to another, you need to think carefully about whether the value you plan to represent can be stored in the new type.